Consider a unit square sitting in a regular number plane. Then consider a point inside that square, and I'll ask you, what's the vertex of the square closest to that point? It's plain to see when it's drawn on screen, it's right here. Now I'll ask a more complicated question. What's the furthest a point inside the square can be from every vertex? I'll illustrate the minimum distance from a point to a vertex on screen. What we're looking for is the maximum length of that line. You may intuitively think that this maximum distance is achieved when the point is smack dab in the middle of the square. And you'd be right. We reach a distance of square root of 2 over 2 from any vertex. Let's turn things up a notch. What happens if I start rotating two of the edges, which we can see as vectors, around the origin and looking at the parallelogram they describe? For the heck of it, let's also say I can make these edges of any length smaller than 1. Then, among all of these related yet distinct shapes, what's the furthest a point can be from every vertex? On an intuitive level, if you stretch the parallelogram in one direction, it's being contracted in the other. So the configuration that puts vertices as far apart from one another as possible remains the perfect square, which yields the same overall upper bound of square root of 2 over 2. This problem can also be posed in 3 dimensions with only the necessary changes. Given some parallelepiped, the edge lengths of which are inferior to 1, what is the furthest a point inside the shape can be from every vertex? Using the same intuitive argument of contraction as before, you may conjecture the upper bound to be reached when you consider the center of a perfect cube, which is a distance of square root of 3 over 2 away from every vertex. In 2D, the question was about parallelograms. In 3D, it was about parallelepipeds. But nothing is stopping us from extending it to higher dimensions, even if I'm unable to provide accurate visuals for these. If we consider 4 vectors of length less than 1, they trace out a unique 4D equivalent of a parallelepiped, represented by this messy whirl of colors. And we can ask our question again. How far can a point inside the shape be from every vertex? Slight terminology aside, for dimensions higher than 3, the generalization of a parallelogram and parallelepiped is called a parallelotope. Since we're on a roll here, you might think of looking at the center of the 4D hypercube. The center of a 4D hypercube is at a distance square root of 4 over 2, or just 1 from each of the vertices. In fact, for an n-dimensional hypercube, it's rather easily shown that the distance from a given vertex to the center is square root of n over 2. With this in mind, I think you are now in a position to make a full-blown conjecture in the general n-dimensional case. Here's how you might state it. Given an n-dimensional parallelotope, the furthest a point inside of it can be from every vertex is square root of n over 2, with the equality reached in the case of a point at the center of the n-dimensional hypercube. To make this a tad more rigorous, we consider v1 through vn vectors of length less than 1, which I'll call the basis of the parallelotope for simplicity. Then the set of vertices is exactly given by the choices of which basis vectors you add and which ones you don't, as shown here in 2D. Here's how you might write that formally. Any given coefficient can be 0 or 1, 0 meaning don't include that basis vector, and 1 meaning do include it. What's nice about this way of writing is that it's easily generalized to higher dimensions. Like so. Let's keep this definition around somewhere in the corner of our heads. Now, notice that every point inside the parallelogram can be described by a combination of the basis vectors, each scaled down by factors between 0 and 1. I'll write down formally P, the set of the points inside the parallelogram. It's very much like before, except the coefficient can be any real number between 0 and 1. Likewise, it can be easily generalized to higher dimensions. Now, the statement of the problem is just the mathematical translation of what we said earlier. Given a point inside the parallelotope, there exists some vertex at a distance less than or equal to square root of n over 2 from the point. Take a moment to understand and appreciate how we got from the geometric statement to the symbolic one. Okay, so now we've reached the problem in its full generality and we've gotten an intuition of why the statement is like this. Still, how on earth do you even approach this problem with all of these moving parts? I'll quickly go over some ideas you might be having right now. You might think of performing induction on the dimension. Well, good luck. If it does work, it's non-trivial at least. What about rounding down the coordinates of the point to identify the closest vertex? That works fine on a cube, not so much when the shapes get a bit more distorted. However, the idea itself is not completely rubbish. We're actually going to use something that you probably don't even think counts as a problem-solving method. What is probability about? If I were to ask this question to a random person on the street, it's very likely they would say something along the lines of, it's a way to quantify randomness. Perhaps you yourself would also answer something similar. My intent here is not to argue that this perception is wrong. It's a good way to conceptualize and rigorously deal with randomness, which is paradoxically something that tends to elude rigor and determinism. I don't think there's a significantly better way of teaching the concept. But not to be outdone, what I want to show you is that probability is not merely limited to questions about colored balls, and that in many ways the mathematical tools it uses lend themselves to neatly solving seemingly unrelated problems. If you've read the title of this video, and I certainly hope you have by now, you've already foreseen what I'm getting at here. Probability is going to be the key to unlocking this complex problem about higher dimensional geometry out of all things. Is it obvious from reading the statement of the problem? No, not even close. The only reason I knew that this problem could be approached in this way is because my teacher commented on it in a remark before the statement of the exercise. But even with this hint, how does one go about this? Let's go back to 2 dimensions. Suppose we have a point inside of this rather distorted parallelogram. What we would ideally like is to find a way to identify the closest vertex. But here, unlike in more simple cases, the closest vertex isn't obtained by rounding down the coordinates of the point. Furthermore, if we insist on rounding down the coordinates, we get a distance greater than square root of 2 over 2. This means a deterministic way to identify the closest vertex would have to depend on the coordinates of the point, as well as the specific choices of the basis vectors, which only get worse in higher dimensions. All of this in a non-trivial way that would result in an extremely complicated formula for the distance. This doesn't look like the right approach. We're confronted with a purely deterministic problem that looks impossible to approach by usual means, and an indication that probability is useful in solving it. All of this seems disjointed, but applying probability in deterministic context has a name: a Monte Carlo method. Monte Carlo methods vary in nature. They follow a common pattern. First, define a set of inputs. Second, generate a large number of inputs randomly based on a fixed probability distribution. Third, perform a deterministic operation on these inputs. And finally, aggregate the results. But here we're not performing a computation, we're constructing a proof. Key adaptations of the method have to be made. Sampling a large number of inputs is just a way to algorithmically approximate the properties of random variables, which we are able to work with as is in mathematics. The deterministic operation can likewise be performed on the random variables themselves, rather than their simulations. If you already know what random variables and expected values are, skip to the timestamp on screen. If you don't know what random variables are, you can see them as a quantity that can be observed as much as you want and take on different values each time you observe it. You can't really make statements about the value a random variable equals, only about its probability of equaling a certain value. The set of values a random variable can be and with what probability it equals each value is called its distribution, and determines it uniquely. One distribution I will frequently use is called the Bernoulli distribution. We say that a random variable called x follows the Bernoulli distribution of parameter p, written with this funky arrow, if it has a probability p of equaling 1 and a probability 1 minus p of equaling 0. Note that 0 and 1 are the only values it can equal. For example, taking p equals 1/2 is how you would mathematically model a flip of a fair coin. In probability theory, the theoretical average value of a random variable is called its expected value, or expectation. More precisely, it's defined as the sum of every value the variable can equal, weighted by the probability that it equals that particular value. Fortunately for intuition, if you were to sample a variable a large number of times and average the results, you'd tend towards the expected value. We still have to figure out what all of these steps are in the context of our parallelotope problem. Let us start with steps 3 and 4, because they're actually quite a bit easier than step 2. For step 3, since step 2 would get us a distribution of vertices, and we're interested in the distance of vertices from the point, it's natural for the distance from the point to be our deterministic operation. If v is a random variable that gives vertices, the norm of v minus p is also a random variable that gives the distance between a vertex and p. I'll write it d for distance from now on. Yes, we do like to give things sensible names in math. Anyhow, that leaves us with step 4. Now, there are many ways of studying random variables, so let's start with an approach on the simpler side. What if we just computed the expected value of d? Recall, it's really just a theoretical average. If we find that this average is less than square root of n over 2, we're done, because that means there must be at least one vertex at a lesser or equal distance than this. It's like how having an average grade of 10 out of 20 means you have at least one grade that's less than 10. You might ask, how do we know this is going to work? That's a great question, and I'll answer it for you. You don't. It's arguably a leap of faith. But in mathematics, you just have to try things and see how they work out. You rarely find the correct strategy on the first try. Going back to our steps, our set of inputs is going to be the set of vertices, our deterministic operation is going to be the distance to the point, and our aggregation operation is going to be the expected value. All that's left to figure out is the distribution. Now, notice that finding a distribution that might work is a far less restrictive task than finding the closest vertex. Because instead of trying to identify the perfect vertex that would yield an answer, we can just guess some vertices that are going to be close enough to the point on average. And what better way of being close to the point on average is there than having the expected value be the point itself? That was a bit of a mouthful. Let me rephrase. Let's try to find a distribution of vertices v such that the expected value of the vertices it chooses is the point itself. The expected value doesn't have to be one of the vertices, in the same way that having grades 10 and 20 gives you an average grade of 15, which isn't a grade you got. A key fact about Bernoulli variables that I want to draw your attention to is that their expected value is precisely their parameter. This follows immediately from the definition of the expected value as a weighted sum, but let's get a gut feeling for this, shall we? The higher the probability of x equals 1 is, the more the average is going to be skewed towards 1. The lesser that probability, the more the average is going to be skewed towards 0. This remains true if we multiply a Bernoulli variable by a vector to get a vector-valued random variable. The expected value can still be defined because we can scale and add vectors together just fine. Here, if the parameter is p, then the expected value of x times u is p times u. But a key fact about the expected value is that it's additive. If you have two random variables x and y, you can consider x plus y, the random variable you get by summing outcomes of x and y with the appropriate probabilities. And now we can say that the expected value of the sum is equal to the sum of the expected values. It looks innocent enough, but it's rather hard to prove, especially when x and y can take on infinitely many values. Let's keep this fact in mind. We previously saw that we could scale a vector by multiplying it with a Bernoulli variable and then taking the expected value. Let's now consider two Bernoulli variables of different parameters and multiply them with two different vectors. By the additivity of the expected value, we can add these two variables together, and the expected value of the result will be the sum of the expected value. This seamlessly generalizes to any number of vectors and variables. But look, if the vectors are the basis of a parallelotope, the random variable will only be equal to vertices. And by tweaking the parameters, we can get its expected value to be any point inside the parallelotope, which is precisely the kind of distribution we had set out to construct. Let's review. Multiplying a vector by a Bernoulli variable makes its expected value some multiple of that vector, determined by the parameter. By multiplying each of the basis vectors by Bernoulli variables and adding the results, we get a random variable, the expected value of which is the point inside the parallelotope. Let's visualize what's actually happening in 2 dimensions. If we have a point way in the top left corner of this parallelogram, the probability of adding v1 will be low, the probability of adding v2 will be high. On the balance, this vertex will be picked more often than the others. Now that we have our distribution, let's finish things up. Contrary to popular belief, pure mathematics isn't devoid of computation. Far from it. In fact, many proofs, including this one, just reduce a problem statement down to a computation that's left to be performed. With this out of the way, the moment you've all been waiting for. Computing the expected value of the distance between our variable and the point, and checking whether it's less than or equal to square root of n over 2. Unfortunately, there are some details that I will have to skip, because explaining them would take a bit too long. I'll put the names of the properties I'm using in brackets if you want to follow along and investigate them on your own. Let's slightly change the inequality to involve the squared norm. This is because the squared norm of a vector is simply the dot product of it with itself, and not having square roots in the way is nice. For homework, check that this is in fact equivalent to our original problem. Now relax and let the computation happen. We're almost there. The nail in the coffin of this proof is a little analysis fact that I will leave also as homework. The maximum of the function x times y minus x is 1/4, reached at x equals 1/2. Using this and summing it all, we get that the expected value of the squared norm is less than or equal to n over 4. So there must be some vertex v such that the distance squared to p is less than or equal to n over 4. This completes the proof. There's one very important fact about this that I want you to remember. This was anything but obvious. I don't see how this proof strategy could have naturally occurred to anyone in the first place. But as for solving it, here's something that might have caught your attention. Exactly how would one think of using the particular distribution I suggested, even with the indication about probability? Well, the most astute among you may have noticed that the coordinates of the various points I introduced often use the letter p, which is usually associated with probability. This was already the case in the original problem statement, And in my personal case, it made me think, hey, what would happen if I used the coordinates as probabilities? And the rest followed from there. But any way to get to the result is as good as any other, and the best one will be the one you wind up finding. For all I know, there's a very pretty and easier to follow proof of this theorem without any use of probability whatsoever. But it wouldn't have been as beautiful as this. We just proved a problem about abstract, sibylline and dimensional objects using probability, used to describe randomness. The main takeaway is that probability was never the subject here. It was the method. Allow me to end on a personal note. My math teacher this past year was, in my opinion, the best math teacher I ever had. Top of just being someone I'm really glad to have met. He constantly marvels at everything and anything, even things that most people would consider exceedingly mundane. He has that sort of childlike fascination, which made learning and being taught by him all the more memorable. He's out there in the best possible way I can think of, to the point that it wouldn't even surprise me that much if the proof I just presented in this video had naturally occurred to him. When it comes to probability, he has a peculiar kind of deference. He holds it in a certain high regard. A classmate of mine asked him whether he considered probability to be a part of analysis or algebra, and he broadly gestured and said there was something beyond that, and it didn't fall in one of these two categories. He's retiring this year, actually, and what I wished to do through this video was pay him a sort of tribute. And I hope I made you understand his fascination for the world and for probability at least a little bit more. I thank you all for watching.